Hello, my name is Michał Włodarczyk, and I'm gonna talk about optimal polynomial time compression for Boolean Max CSP, which is a joint work with Bart Jansen. I will start with a short introduction to constraint satisfaction problems, which is a family of problems of the form find an assignment to the variables that would satisfy all the constraints. And for different kinds of constraints, we obtain different problems, with some classic examples being trisat, where a constraint can be of form at least one of x, y, z is true. Not all equal sat, where at least one of three variables should be true, but at least one should be also false. Or 1 in 3 sat, where exactly one variable should be true. An instance of trisat might look like this. And if we wanted to phrase it in terms of modern CSP language, we would say that we have variables x, y, z, w, and these three constraints. In general, we are not allowed to write a negation operator. So instead of that, we can have several relations. For example, or plus minus minus, representing disjunction with second and third argument negated. In this talk, I'm going to focus on Boolean CSP, so the variables can take only two values, 0 and 1. This idea of constraint types can be formalized with a notion of constraint language, which is a finite set of Boolean relations, and each relation is a finite set of Boolean tuples of fixed dimension. In this example, we see four relations that express the 1 in 3 sat problem. For example, relation R0 says that exactly one of the variables x, y, z equals 1. And if we wanted to express a clause with first and second argument negated, we can use relation R2, where the first and second columns are negated. And for a given constraint language, we refer to a problem where such a constraints might appear as CSP gamma. For in these terms, there is a nice classification theorem which says that CSP gamma can be either polytime solvable or NP-hard, so there is no middle ground, and provides structural properties on gamma for CSP gamma to be polytime solvable. In this talk, we are going to focus on the compression perspective. So when we work with NP-hard problem, we can consider a polynomial time preprocessing algorithm that produces an equivalent instance of potentially smaller size. So it can be useful to first compress an instance and then use a SAT solver to solve it brutally. From a parameterized perspective, it is interesting to understand what is the best compression size for CSP depending on gamma. And this idea of compression of kernelization originates from parameterized complexity. And here the parameter that governs the size of the kernel or the compressed instance is the number of variables n. So there are some known results on the compressibility of CSP. And first observe that the DSAT problem can be trivially compressed to n to the power of d bits, because there are essentially n to the power of the d tuples and that many possible distinct constraints. It is less trivial to see that one cannot get any better compression. There is a lower bound saying that for every dsat, for d at least 3, if we could improve this compression bound just a little, this would imply that NP is contained in ClanP by poly, which would imply collapse of the polynomial hierarchy. The assumption that NP is not contained in ClanP by poly is now a standard assumption in the compression theory. For other CSPs, we know, for example, that one in dsat is pretty easy from compression perspective, because for any constant d, there is n log n bit compression. The d not all equal sat is slightly easier than dsat, because we can compress it into n to the power of d minus 1 log n bits, and also this bound is tight. More generally, when we have a constraint of the form that we are given a subset of integers d, and we require the number of true literals to belong to the set d, we can compress it to n to the power of size of d log n bits, but this is not always tight. Also, we know what are the hardest T-ARI Boolean CSPs, so that there is there is the same lower bound as for dsat, and these are these CSPs that have a constraint with exactly one falsifying assignment, so the same as for dsat. There is also a full classification of Boolean CSP with max arity 3, but there is no general classification yet. And now I'm going to talk about Max CSP, which is a variant of this problem where we not necessarily want to satisfy all the constraints, but only to maximize the number of satisfied constraints at once. And observe that it might be the case that the decision CSP is polytime solvable, but the Max CSP is NP-hard as for 2-sat. Since for Max CSP it matters how many times each constraint repeats, we allow each constraint to be associated with integer weights of a polynomial magnitude. And the concrete decision problem is that as follows. We are given a set of variables, a family of weighted constraints from the language gamma, and integer t, and we ask, is there an assignment that would satisfy constraints of total weight at least t? And our motivation from a compression point of view is for a given gamma, what is the best compression upper bound n to d depending on gamma. The Max CSP admits a similar dichotomy theorem as the regular CSP, and we also know that there are some simple properties of gamma that govern whether it is polytime solvable or NP-hard. And our main result is an extension of this theorem. Namely, we show that for any finite Boolean constraint language gamma, there is an integer that Max CSP gamma admits an n to the power of d log n compression, but as long as it is NP-hard, there is a matching lower bound. So we cannot break the n to d barrier, assuming NP is not contained in ClanP by poly. And two remarks: that this lower bound works also in the same setting as the classification theorem above. So the hardness works also where the weights are only positive. And this compression can be turned into a kernelization, so a compression to the instance of the very same problem, with a little caveat that the range of weights needs to be slightly increased. The main tool that we exploit in the proof of this theorem is the notion of characteristic polynomial. For a given Boolean relation, its characteristic polynomial is a unique k-variate multilinear polynomial such that whenever a k-tuple belongs to the relation R, the polynomial should evaluate to 1, and otherwise it should evaluate to 0. It turns out that such a polynomial always exists and it is unique. For example, we can see characteristic polynomials for relations 3 or 3 not all equal, and 1 in 3. And we can see that for 3 or it is the polynomial evaluates to 0 only when all the arguments are 0. The not all equal polynomial is similar, but it should also evaluate to 0 while all the arguments are 1, so we shave off this last term. And what is interesting, this second polynomial has a lower degree, and it indicates that it should be simpler from the perspective of compression. And indeed, since the characteristic polynomial is 0, 1 valued, constraints are applied to variables x1, xk with weight w, contributes to the total weight of the solution exactly w times a value of this characteristic polynomial evaluated on these variables. Hence, instance of Max CSP gamma can be represented as a sum of the characteristic polynomials, and the optimization task is equivalent to maximization of this polynomial, with a degree given by a maximal degree of a characteristic polynomial for a relation in gamma. We refer to this parameter as degree of gamma, and it turns out that this is the parameter that governs the compressibility of Max CSP gamma. In particular, for a compression upper bound, we can see that such a polynomial has n to the power of the different monomials, and since weights are of polynomial magnitude, we can encode them in log n bits, so this whole polynomial can be encoded in n to the log n bits. It is less trivial to see that this parameter degree of gamma also provides a lower bound. And in order to prove a lower bound, we construct a reduction from max dsat to max CSP gamma, and we take advantage of the fact that already a decision version of dsat has established lower bound. And the idea in this reduction is to express one characteristic polynomial with the help of other one. For example, consider these two characteristic polynomials for the relation 3OR and 1 in 3. And this first polynomial can be written as a linear combination of polynomials expressible with 1 in 3 by replacing some arguments with a constant 0. This is a polynomial identity, so the coefficients at each monomial match. So this equality holds for any assignment to these variables, in particular for any Boolean assignment. And in general, we show that such a family of polynomials where we replace some variables with a constant 0, 1, span the linear space of bounded degree multilinear polynomials over Q. So this gives a way to construct a reduction. So we can take a polynomial given by an instance of Max CSP gamma 1 and express each characteristic polynomial from gamma 1 with a linear combination of characteristic polynomials from gamma 2. And this is possible as long as we have this relation between degrees. And there are several obstacles in turning this into a proper reduction. The first one is that we need to get rid of these constants 0 and 1. So we need to introduce a new variable and force it to be always equal to 0 or 1. So we need some gadgets to enforce this property in every optimal solution. Next, these weights that we obtain in this created polynomial can be non-integer and they can be negative. And for our lower bounds purposes, we would like to end up with only positive weights. And in this construction, we can increase the number of the variables only by a constant factor because we want to preserve this polynomial bound on the compression size. And it is not always possible to make this reduction work because Max CSP gamma can be polytime solvable, and then we shouldn't be able to construct any compression lower bounds. But let's recall this dichotomy theorem, which gives structural properties on gamma that makes Max CSP gamma NP hard. And similarly, as in the proof of this dichotomy theorem, we exploit these properties in order to make appropriate gadgets. So I'm not going to define what these properties are, but these are some properties that says that gamma is sophisticated enough. And the most technical effort in our paper is using these properties to gadgetize these like obstacles and make the reduction work. So once we are able to identify the optimal compression size for Max CSP gamma, we can take a look how this works with the examples that we've seen so far. And Max CSP can be only harder than decision CSP. And for example, for 1 in D SAT and the linear SAT, we can get almost linear compression for decision CSP, but for Max CSP we get the same lower bound as for DSAT. And interesting phenomenon occurs for D not all equal SAT, because the degree of the characteristic polynomial is D when D is even, and D minus 1 when it's odd. So 3 not all equal SAT admits n square compression, but 4 not all equal SAT requires n to the power of 4 bits. And there is additional corollary from our framework of reductions, which concerns exponential time algorithms for Max CSP. And even though the decision version of 3SAT can be solved slightly faster than 2 to the power of n, there is a conjecture that for Max 3SAT it is impossible to improve upon trivial algorithm, and essentially we cannot improve this to the power of n running time. So our reductions imply that if we could solve some NP-hard Max CSP gamma in time better than 2 to the power of n, it would imply a similar improvement for some Max DSAT. So this degree of gamma also identifies an equivalency class for an optimal running time. And this corollary is possible because some of our reductions are of this form, where the parameter transformation only add some constant, so such a transformation preserves this running time. Let me conclude that our results provide a complete characterization of optimal compression size for Boolean Max CSP, and this is given by the maximal degree of a characteristic polynomial in gamma. For larger domains, it is unclear what's the right tool to characterize the optimal compression, and characteristic polynomials are not so easy to define. We don't know how to define them, so they would be unique. So this approach doesn't work anymore. Also, we have assumed in this work that the weights are polynomial, so they can be encoded in log n bits. But if we considered instances with exponential weights, then we also need polynomially many bits to encode them, and it is not known what's the optimal way to compress such huge weights. And finally, we don't know what's the right tool to understand the optimal compressibility for decision CSP, and there is a rich spectrum of techniques to obtain upper bounds in here, and we don't know which techniques gives like the best understanding, and we often don't have matching lower bounds. So that's all. Thank you for your attention. I hope you like the talk, and see you at the Q&A.